Welcome to Math, where problems are no problem. You've probably heard that ice cream sales and shark attacks are correlated, which sounds like ice cream is dangerous, but really it just means both go up in summer. That's correlation. Regression is the next step. It's turning that relationship into an actual equation you can use to predict one thing from another. Today we'll figure out exactly where one ends and the other begins, using one simple example the whole way through. Here's the everyday version first. Imagine two joggers running side by side, connected by a stretchy leash. Correlation is just noticing. When one speeds up, does the other speed up too? Regression is drawing the actual rule for the leash. If runner A goes this fast, runner B goes exactly this fast. So you can predict runner B's speed just by watching runner A. Let's ground this in real numbers. Say we track 5 students. How many hours each one studied, and what score they got on a test. Hours studied is one variable, a quantity that changes from person to person. Test score is the other variable. Our data looks like this: 1 hour, 50 points. 2 hours, 60 points. 3 hours, 65 points. 4 hours, 70 points. 5 hours, 80 points. First, let's plot these as dots on a graph. Hours along the bottom, score up the side. This picture is called a scatter plot. Literally just your data points scattered on a grid. Looking at this scatter plot, you can already see the dots drift upward together. More studying, higher score. That upward drift is what correlation measures. Specifically, correlation asks 2 questions. How strong is the relationship, and which direction does it go? A number called the correlation coefficient, usually written as the letter R, captures both answers in a single value between -1 and +1. If R is close to +1, the two variables rise together tightly. If it's close to -1, one rises while the other falls. If R is near 0, there's basically no relationship at all, like shoe size and favorite color. Let's actually calculate it for our study hours data, because seeing the arithmetic makes it click. First, we find the average hours studied, which is 3, and the average score, which is 65. Then for each student, we look at how far their hours are from the average, and how far their score is from the average, multiply those two differences together, and add everything up. Doing that here gives us a total of 70. We also square and add up the hours differences, getting 10, and square and add up the score differences, getting 500. Correlation is that 70 divided by the square root of 10 times 500. 10 times 500 is 5,000, and the square root of 5,000 is about 70.7. So our correlation is 70 divided by 70.7, which comes out to about 0.99. An R of 0.99 is about as strong and positive as real data ever gets. These two variables are moving together almost perfectly. But here's the catch, and it's the whole point of this video. Correlation only tells you that they move together and how strongly. It never gives you a formula to actually predict a score from a given number of study hours. For that, we need regression. Regression means fitting a straight line through the scatter plot that best represents the trend. This is called the line of best fit because it's the one line that sits as close as possible to all the dots at once, even though it probably won't pass through any of them exactly. Every straight line has 2 ingredients: a slope, which tells you how steeply it rises for each step to the right, and an intercept, which tells you where the line crosses the vertical axis when the input is 0. Using the same numbers from before, the slope for our line turns out to be 70 divided by 10, which is 7, meaning each extra hour of studying predicts about 7 more points on the test. The intercept comes out to 65 minus 7 times 3, which is 65 minus 21, giving us 44. So our regression equation is predicted score equals 7 times hours studied plus 44. Now watch what this buys us that correlation alone never could. Suppose a new student tells you they studied 3.5 hours. Plug it in. 7 times 3.5 is 24.5, plus 44 gives 68.5. We just predicted a specific test score for someone who wasn't even in our original data. That's regression's whole job. Correlation tells you a relationship exists and how strong it is. Regression hands you the actual predicting machine. Let's double-check our line actually fits reasonably well. Plug in 1 hour. 7 times 1 is 7, plus 44 is 51. Our real data point was 50, so we're off by just 1 point. Plug in 5 hours. 7 times 5 is 35, plus 44 is 79. The real value was 80, off by only 1 again. A line that lands within a point of the real data on both ends is doing its job nicely. So here's the difference, cleanly. Correlation is a single number summarizing how strongly two things move together. It's the observation. Regression is the equation built from that relationship. It's the prediction tool. You could think of correlation as noticing your two joggers tend to speed up together, and regression as the actual formula that tells you runner B's exact speed once you clock runner A. If this helped, the next video covers how to interpret what the slope and intercept in a regression equation actually mean in real-world terms. And if you're finding these explanations useful, subscribing helps more people stumble onto them too.